Okay, so let's begin. Yes, so welcome Fabian Immler from Carnegie Mellon. So he'll talk on formal mathematics and the proof of chaos.
Yes, thank you for the introduction. Thanks for the invitation. It's a great pleasure to be here and talk to mathematicians, actually. It's something that we should do more often, I guess, in my community. So I think I should say a bit more about where I come from. So I'm a computer scientist by training, did my PhD in the chair for logic and verification. And so we are concerned with is what I call here formal verification, and the motivation behind why do we need formal verification is, if you know, that computer programs have bugs. There's almost no computer program without bugs. And formal verification is a technique which can prove the absence of bugs. And
if it doesn't have bugs itself.
If it doesn't have bugs, yes. Would be fun otherwise. What do I mean by that? You do it in a rigorous calculus, and you sort of reduce the correctness of the computer program to the very axioms of the logic of your rigorous calculus. And this sort of reducing things to the axioms of logic is also relevant for mathematics, I would say. This is what I call formal proof in mathematics. So we can use these axioms of logic as foundations of mathematics. These foundations can provide absolutely rigorous proofs. So there'll be no doubt about the correctness of a proof. Think about perhaps checking proofs in math journals completely automatically if you do the proofs in such a system. Another aspect where this is relevant is computer-assisted proofs. And a computer-assisted proof is a proof where part of the reasoning has been carried out by a computer program. So this is a proof. Those proofs usually involve large case distinctions that are discharged by a computer or numerical computations. And this is something that traditional mathematical point of view, this is different from a traditional proof because it's much bigger and usually not surveyable anymore by a human. What I personally have been working on is I worked on formally verifying numerical algorithms, like proving the numerical algorithms correct. In particular, numerical algorithms for solving or approximating ODEs.
What do you mean by numerical algorithm?
I'll go into it in a bit more detail, but numerical algorithm, I mean computing with finite precision numbers, and verifying the correctness of approximate algorithms is a bit subtle, at least. But there the idea is to compute bounds on sort of the real value that you want to approximate.
That means to take into account the round-off errors?
Yes. That will all be taken into account by the verification. Yes, and I've applied this to one particular computer-assisted proof in the field of dynamical systems, namely Smale's 14th problem. It's about the Lorenz equations. And along those lines, I will structure this presentation today. So first, I'll talk a bit about formalization of mathematics, like how can we or how do we build mathematics on firm foundations. I'll talk a little bit about examples of computer-assisted proofs, talk a bit more about Smale's 14th problem, what it's about and how it has been proved and how I verified it. And in the end, I'll also talk about the implementation and actual verification of this verified ODE solver. Yeah, so let me start with formalization of mathematics. What is a formal proof? So you pick a formalism and you reason in a strict calculus, and this reasoning is mechanically checkable. So for example, if you pick as formalism predicate logic and natural deduction, then a formal proof of all men are mortal. So this would be an axiom written in the formalism in predicate logic. So for all x, if x is a man, then x is mortal. Yes, so all men are mortal, and Socrates is a man, which is another axiom. Then you can come up with a proof that Socrates is mortal by applying rules of the calculus. So here, modus ponens, if A implies B and you know A, then it follows. So that's what I mean by formal proof. Or something like that. And with something like that, one can have really ambitious visions for mathematics. So perhaps we'll do all of mathematics in such a formalism. Because then you could check all proofs that are being submitted to journals, for example, completely automatically. So you just need to, like the role of a reviewer, a journal, for example, would just be to look at the definitions, or are the definitions right? Is the problem interesting? But the correctness of proofs is sort of can be left to the computer.
This sounds like this is what actually done nowadays, often without using the computer. Like you don't check the proofs anyway.
Yes. So,
yes, you're suggesting to improve this process,
yes,
to actually check the proofs.
Yes.
I'm
And
not sure I would be in favor of it. You would delay the process of referring papers.
Do you think so?
Yes.
If the computer is maybe the computer can do it faster than
Yeah, I
human being
think
deciding the
you
process.
just add layers of administrative things in between.
So this would require some assistance to retype the paper into the format that you're thinking process.
yes, for example, or very ambitious at some point, perhaps this formalism
Probably
is not harder to write than
The
later.
computer can understand type.
Yeah, but what do you do with this, with all the language? In practice, how hard is it?
I'll give some examples to give an impression of where we are in this, in reaching this ambitious view. Another advantage would be that if sort of all of mathematics were built in one formalism that can be understood by a computer, you can also search this library and search for connections. So, for example, you know that this predicate of mortality is a concept, and you can search in your library, what do I know about mortality? And yes, yeah.
Well, I mean, you don't have to know the semantics. This is the formal proof. I don't have to understand what mortal mean or even what man means.
Yes,
Semantics
but I mean,
cannot be
Or
put
even
into
what
this.
Socrates, who Socrates is, right?
I mean, you can search for formal entities.
Right.
That's the idea.
They're easy to be defined.
Yes.
William in there instead of Socrates.
Right, exactly.
Yes. So about formalization of mathematics. By formalization of mathematics, I mean putting mathematics in this rigorous, in a rigorous formalism. It's very labor intensive, especially because sort of need to construct everything from first principles. So start from the axioms of set theory, for example, and then need to construct everything. So
how long did it take you to when you were checking that proof? To retype it into a format that computer can read.
perhaps I can say a bit more about this. So this is sort of an example of how we construct mathematics from axioms of the underlying logic. So from zero and the successor function, you construct natural numbers, taking quotients, you get integers, taking quotients, you get rational numbers. How long does all of this take? So theorem provers, which is systems checking such proofs, been around since the 60s, 70s. First libraries for real analysis, I don't know, were developed perhaps in the early 2000s. And so I did my work sort of building on a library for multivariate analysis, vector analysis, formalizing theory of ODEs. And this includes, I don't know, perhaps 1, 2, 3, 4 chapters of an undergraduate level textbook of ODEs. And this work took me, it's hard to say, perhaps 2 years.
No, I mean, when you work, so you wanted to verify a particular proof, right?
Yes.
How long did it take you to retype it into the format that's your
The statement or the proof?
No, to get the final product. So you have someone else's proof, you wanted to verify it, so you transform it into your system. So that process of transformation that you can run your program on. How long does it?
Are you verifying somebody's proof, or actually the computer produces a proof from the statement of the theorem?
So I produce a proof from the statement of the theorem.
Yeah.
So
Right. So it's not verifying your proof. It's giving you a proof.
It's sort of repeating the proof.
Probably most
And
proofs are formalized.
So in this case, so formalizing ODEs is about repeating proofs that you find in textbooks, for example. And that's relatively
this process, but when you
Yes.
So he had a computer system proof.
Yes.
You wanted to verify that it's correct,
Yes.
and maybe you found some bugs. But in order to verify that that proof was correct, there was some transition process.
Yes. So I needed to implement this
Right.
program that Tucker used. Yes.
Okay, but and just the program, and the rest is
Just the program and differential equations, because this is sort of the specification of what the algorithm is supposed to do. All of that, I did that during my PhD, which was 5 years.
But he already had a program. Why would you need to implement it?
Because I need to implement it in a way that's amenable to formal verification.
I see.
So there's no hope to take a program that's not written with verification in mind and verify that. So it's much easier to rewrite a program.
And was it easier that rewriting? It's not the major
Yeah,
part of the
no,
work.
it's, I don't know, similar to you read a text somewhere and you type it up in LaTeX,
Okay.
for example.
Okay, so that's nice.
I mean,
Okay.
Proving is a bit more effort. But yeah, perhaps I can give some intuition about that too. So all of these proof checking and dealing with formal entities is done in so-called proof assistants, and there are lots of different proof assistants in the world. They build on different foundations, so some use set theory as in first order logic as underlying the foundation, some use type theory, some use simple type theory. Here I just named some. And all of those theorem provers have been used for very different verification projects, including hardware verification, verification of compilers, formalization of analysis, algebra, floating point numbers, CompCert is a verified compiler, it's an operating system kernel that's been verified. So these proof assistants are relatively mature in the sense that there are ambitious software systems and algorithms that can be verified at the current state of research. the proof assistant that I'm using is, it's called Isabelle, HOL. Its foundation is higher order logic. It doesn't have dependent types, which makes the logic a bit less expressive or restrictive at times, but it makes formalization easier sometimes, and it helps the system to automate proofs. It has a big library of analysis, so on which I built, and the proofs that you write in the system are structured. So in some sense they look, or sometimes one can recognize structure from a, for example, textbook proof in Isabelle. So the idea is that those proofs are not just readable or understandable by the system, but also by a human that looks at it from a higher level.
What do you mean by no dependent types?
There's different type theories. You can see as foundation of mathematics, and usually when you speak of type theory, you mean dependent type theory, so that types may depend on other types. In higher order logic, there's a distinction between terms and types must not depend on terms. So there's a bit of a layering.
So you use higher order logic?
Yes, I use higher order logic.
So you can have sets, variables of sets and things like that?
Yes. And yeah, it's perfectly fine for formalizing real analysis. I wanted to give one concrete example how formal proofs in Isabelle look like, sort of in the wild. So I took this. This is from some course notes by Jeremy Orloff. It's Lerch's Lemma. It's about the uniqueness of the Laplace transform. So some conditions such that this function, a continuous function, is 0 if all of those integrals are 0. And the proof is, I don't know, take a continuous function, you know that it's the uniform limit of a sequence of polynomials. Then you can reason about it with intervals, taking limits, and then things 0. And what I picked up here is a formal proof in the Isabelle proof assistant of this lemma. It's a bit more text, but I would say it's not like overly more text. So, and in pink, you see some of those intermediate statements that provide structure to the proofs. So, I don't know. This is, for example, a uniform limit of polynomial functions. You can say that the integral of something is 0, and so everything in between those pink statements, much of this is proofs that are automated by the system. It says auto. This performs some rewriting, simplification, does some kind of limited proof search.
But this is based on that you would deal with proofs that use textbook statements. But often you see that the paper would use other people's statements in some other papers.
Yes.
You would have to retype all of that as well.
So, yes, so that's the thing. That's what I said earlier. It's labor intensive, so you need to go back to the foundation. So if you want to use a result, you need to sort of formalize this result as well.
But presumably you have more or less a library of already formalized things that you
Yes, exactly. Exactly. So, the state where I started was a reasonably good library of real analysis, and I built differential equations on top of that. And so when you have when all of the foundations are there, the correspondence between an informal proof and a formal proof is not 1-to-1, but perhaps a ratio of 5 to 1. So just to give you an idea of what the additional work is that you need to put into formalizing something.
If only textbook statements are used, right?
If all the foundations
Are there?
are there. Yeah, I think I'm going to skip this example. Yes, yeah. Some of the things that I've worked on in formalizing mathematics is, yeah, as I said, differential equations. I've also worked on formalizing smooth manifolds, but it's interesting for dynamical systems. In the work that's going on in the Isabelle community as a whole, or in the AFP. So the AFP stands for Archive of Formal Proof, and that's a library in the internet where, or it's somewhat organized like a journal, so people can submit their formalizations there. They will be reviewed and then they're available for everyone. So you can build your developments on the AFP, for example. And yeah, so also things like measure and probability theory, analytic number theory. Also wanted to mention some other proof assistants, COC, for example. That's another proof assistant. It's a system Isabelle, but has different foundations. So it's a dependent type theory. They are one of the most prominent formalizations for the formalization of the odd order theorem, which took a large group of people a lot of time, but helped in building a large library of algebra. So if you want to do algebra, abstract algebra, COC is probably the right system to use.
What was the theorem?
That every finite group of odd order is solvable. It's sort of one step in the classification of finite simple groups. I don't know too much about it. There's another theorem proving system that I wanted to mention. It's called Lean. It's relatively new and sort of tries to combine the best of the experience that people have gained with, among others, Isabelle and COC. So Isabelle and COC have been around for 30, 40 years. So they carry a bit of legacy with them, but gain a lot of experience with them. And so Lean tries to draw on this experience and try to build a good theorem prover sort of from scratch.
Are you saying that COC has proven the odd order theorem?
Yes. Yes. It was a big project led by Georges Gontier at Microsoft Research. And Lean currently has a very fast-growing and active community. One thing that's notable about Lean is that apparently working mathematicians are getting interested in using it and formalizing their own research level mathematics, actually. So, as I said earlier, is this a vision for the future? Is this an ambitious vision? Kevin Buzzard is a number theorist, analytic number theorist. He says that this development is sort of inevitable, that we're going to do mathematics in formal proof assistance at some point in the future. Because proofs and definitions are getting bigger and bigger. Like you said, proofs aren't checked anymore, actually. And simply because there are too many advantages of doing mathematics formally. You can search and connect things in a computer understandable way. And I think I hinted at the fact that there are lots of, I would call them isolated projects, like the proof of the odd order theorem, or sort of my formalization of ODEs. So when you pick a topic, then we sort of know how to formalize, or that it's possible to formalize also advanced topics. And we also know, like, if there are two isolated projects, we know that we can sort of combine them in a system and work with this combination. But what's missing, or I would say the main point that's missing, is that there is no comprehensive library of sort of all undergraduate mathematics. So single isolated things, but nothing comprehensive. So if you take a graduate level textbook, it's highly likely that you and want to formalize it, it's highly likely that you hit on something which is missing the foundations. Then you will need to spend a lot of time formalizing those. Yeah, perhaps it's not yet the time to do all of mathematics formally, but it still has some, or doing formal proofs has some advantages also for current mathematics, I would say. In particular for computer-assisted proofs. I've said proofs that depend on the output of the computer program and how do you trust this computer program. The idea is formally verified.
You get the computer to produce an example from a theorem that's verified?
Sorry, what?
Can you get the computer to produce an example of a theorem that is verified?
An example?
Yeah, like a group of order 7 is solvable. Take some group of order 7 and prove it's solvable.
Yeah.
You can do that.
Yeah. I'd say you can do that.
How would you do it? Because in a formal system, as you said, it's all formal. Apples and oranges, you throw them as numbers, it's okay. But so the things going on that how do these systems actually encode examples with standard semantics? Numbers are numbers, not apples and oranges or whatever. Right?
Mm-hmm.
How do you create examples?
So maybe the question could be, how is the group of order 7 actually given to the computer to show it is solvable?
Yes.
Just to give number 7, and that is a group? Or is it given by generators and relations? No.
In the end, that's up to the person that formalizes this library. So choosing representations or choosing representations that can be evaluated by the computer then, things like that. So it's up to the person that formalizes.
Can I just say that this is a group of order 7 without telling you anything? Except that it is a group?
You would need to give the proof that it's a...
Then it will come over.
Or somebody has developed the library.
If you give the proof for the all odd numbers, then certainly you should be able to prove it just with 7, right?
Yes. Then you can instantiate this theorem. Then you just need to prove that 7 is odd.
No.
And then there's an eyewitness for that.
Just accept that will cheat. I don't want to see a proof that 7 is odd. Okay.
Yeah,
I give 7 to you.
cheating.
Prove that group is solvable. I
Yes.
give a construction.
Can you follow the proof
Well, the
to
construction...
apply to the number 7 in particular?
The constructions just take the theorem...
Yeah, I can
The
imagine.
theorem for odd order.
I think that would be more interesting actually. That would be a more interesting application. More constructive application. Right.
Well, Bob famously said that the example is more important than the theorem.
Right.
Yeah. What people are doing a lot, or people work a lot on not producing examples, but counterexamples to conjectures. Because usually when you start out formalizing a proof, often you don't get the statement right.
Mm-hmm.
And then you have some automatic search for counterexamples, and it searches for small finite models or countermodels. Then it tells you this theorem doesn't work for 2. Yeah. I'd say for proof development, counterexamples are more important than examples. Actually. Some examples of computer-assisted proofs: the Kepler Conjecture, It's been proved. So it's about what is the densest way to pack spheres in three-dimensional space. It's been proved in 1998 by Thomas Hales and Ferguson. And the computer-assisted part is lots of nonlinear and linear optimization problems. And Hales had trouble getting his proof accepted in the journal because the reviewers said, how would we check that all of those computations are correct? And sort of in response to that, he initiated a project to formally verify all of his computations. Just been completed in 2015 in a combination of the Hall-Light and Isabelle theorem. So yeah, he really did all of those, or solved all of those optimization problems in the formal system. The four-color theorem, stating that every planar graph is four-colorable. It's been proved in the 70s by Ken Appel and Haken. I think this was probably the second very prominent computer-assisted proof. It's mostly graph theory, and the computer program discharges lots and lots of cases in a large case distinction. And this.
But that kind of verification, or for a finite number of cases, has that anything to do with your formalism of mathematics? Or is it just some search kind of algorithm to verify that, take a case and say, okay, that's all right. Take a case, okay, that's all right. And then just cover all the cases. But is that anything to do with your formalism? Logic.
No, ideally it doesn't depend on the logical foundations, right? So you can build mathematics, as I said, you can build it on set theory, you can build it on type theory, and in the end, when you check all of those cases, it doesn't really matter in which formalism.
Suppose in 1976, such formalism doesn't even exist, right?
Yeah.
So they just write computer programs to verify cases, right?
Yes.
So that's not an example of power, let's say, of Isabelle.
No, but it's an example of a proof produced by a computer. But it's not a formal proof.
Okay.
So that's the distinction.
Okay.
So here's a proof, a computer-assisted proof, and here's a formal proof checked by the computer.
Which means to say it checked all the computations in the individual examples.
Yes. And sort of reduced all of them to the axioms. Another computer-assisted proof, we're probably going to talk about this for the rest of this talk, is Smale's 14th problem about the Lorenz attractor. It's been proved in 1998 by Tucker with a combination. So the proof consisted of classical analysis, normal form theory, and also relied on numerical bounds on the flow of the ODE. And this is sort of what I've verified in Isabelle, this computation of numerical bounds, and also what to deduce from that.
Sorry.
Yeah.
Go ahead. So in that case, did the system, did Isabelle, for example, verify that the bounds are correct?
Short answer, yes. Bit longer answer is I implemented an algorithm that computes the bounds, and this algorithm is verified to be correct, that it outputs bounds.
What does an ODE theory look like in this structure? What's like an input? You want to input an equation and an epsilon and a time, and you want to get a solution up to epsilon and time t, or
something like that. Yes. So you give the ODE just as a term, and as input initial value or initial set actually, then this algorithm computes enclosures for the solution. So the output is something that's guaranteed to contain the solution after some time.
And that's, you also input a precision, or you specify the precision in the proof? Or
You also input a precision, yes.
then it may say, I can't do it, or the bound may be ridiculous, or...
Yes, yeah, it could be that the bound gets ridiculous, yes.
Yeah, but what's the meaning of the bound if you can give... you can just give anything.
Well, yes, I mean, of course, so for this Lorenz attractor, I mean, one bound you could give is just some hypercube enclosing the whole thing. But this bound on the flow would not be useful because Tucker deduces some properties from these bounds, namely that the Lorenz attractor is chaotic. And so this is something that I've also verified, that these bounds are sufficient to certify that there's chaos in the system.
So initially, I think the problem was to prove the existence of this contracting bundle.
Yeah.
And now you're talking about specifying that you can find an approximation to an invariant bundle and then prove there is one by some estimates, and you verify all these estimates. And it has to be on a large grid of points in the...
I'll go into it in a bit more detail. Yeah, so yeah, it's one of the...
Prove NP with NP too?
It's one of them,
yeah, it's just, one of Smale's problems for the next century, and one of them was is problem 14 about the Lorenz attractor. It's about the Lorenz equations, this system of three-dimensional system of ODEs. Yes, and what Lorenz did, so he used it to model flows in the atmosphere, and I believe it was one of the first examples or descriptions of chaos in a deterministic system. So he did some finite precision approximate calculations and realized that after some time it had completely different behavior, although the initial conditions were like epsilon close. This sort of coined the term butterfly effect or chaos. It's a prominent example of chaotic dynamical systems. So the Lorenz attractor is sort of on all of the Wikipedia pages related to this. Yes, so the numerical observations were that this structure is chaotic, so small initial deviations produce different long-term behavior. The mathematically precise notion is that there's a strange or hyperbolic attractor. And apparently lots and lots of people have worked on these equations, on the problem. But up until Tucker's work, there haven't been any rigorous proofs or any proofs that this is chaotic. The late 70s, Williams, Guggenheimer, and York came up with a model. It's called the geometric Lorenz attractor. So this is a geometric model of a dynamical system that qualitatively or looks like it behaves similar to the Lorenz system. And it's made up of dynamics, say, in a cube. And in this cube, the dynamics in this cube is governed by a linear ODE, which is called L. And solutions sort of here, solutions flow downward and then spiral left and right and come back. And this model, this is modeled in this geometric model by some closed form expression for how solutions flow from the right back to the top, this G. So this is just some easy analytic expression. which made it possible to analyze the dynamics of this composition G of L. So they could prove that the dynamics of this thing so it's a strange or hyperbolic attractor. Smale's 14th problem is if the behavior of the geometric attractor is the same as the real one. And Tucker's proof from 1998 is so it's actually quite similar to the geometric proof in a way. So he analyzes the Lorenz attractor by introducing a Poincaré section here and then studying the dynamics on this Poincaré section. What does it mean? The Poincaré map is defined as...
Could you go back to a previous slide?
Yes.
So what is the...
This one?
Yeah, so what's the connection between the geometric Lorenz attractors and...
There is none. And that's precisely the problem. It's just the dynamics of this thing look similar to the dynamics of this thing.
I see.
Like
And
qualitatively.
this is the definition of strange geometric attractor. Is that the what's exactly is the definition? What's a property?
I think I'm unable to define it, but one crucial thing is that it's an attracting set, so solutions tend to it. But on this attracting set, solutions diverge.
I think normally speaking, before these types of examples, in ordinary differential equations, the attractors were points, equilibria, or maybe closed orbits, or sometimes invariant tori. So suddenly you get a set that looks like this. It's an attractor, it shows sensitive dependence on initial conditions. It's a very complicated set, and it shares a lot of stability properties. It doesn't go away. This is a big change in
So
perspective.
it's a new kind of example.
A new kind of example of that change is how people think about what ultimate behaviors might look like.
And how sensitive is it to the coefficients? Because he gave concrete coefficients.
Yeah.
No, it's not. It's not very sensitive.
So you can put just any parameters there. Like for
Well, there's a whole theory of what range of parameters.
Well, for certain parameters, there's first integrals for the Laurent system.
So I guess the very fact that you can numerically verify means that there's some range you can play with.
Yes.
Right.
That's almost comes from
So-
the nature of numerical verification.
So this is for a fixed set of parameters, like the classical parameters of Lorenz. And the proof is for some neighborhood around those parameters. To prove that
That's the only way.
the behavior is stable and the only way to do something numerically, actually.
I think it is also a kind of illustration of why weather is so unpredictable.
Yeah.
The system.
That's sort of why it's become
I mean, that's
a
why
popular
people
example.
study the system.
Yeah.
It's from weather.
Isn't it amazing?
Originally,
You can predict this
Yeah.
path of a
That's right.
hurricane,
yeah.
even with a marker.
Well, there are two systems, European and American.
Right, and the magic marker system.
Okay. So to go back to Tucker's proof, his proof is it's quite similar to the geometric model. So with this Poincaré section, you study what does the dynamics do on this Poincaré section. So you start here, flows there, and returns there. So and in the end studies the dynamics on this section sigma. How does he do it? He sort of encloses somewhat the intersection of the attractor with the Poincaré section. He encloses it by a grid of intervals and then computes numerical bounds on how the intervals are propagated by the flow and how they return to the to sigma, to the Poincare section in the end. So this works fine for most part of sigma. Some solutions, particularly those here, they tend towards the origin in infinite time. There's no hope that you can do anything with the numerical methods there, because numerical methods are always finite time. That's why he does some classical analytical proof, normal form theory. So he devised some coordinate change close to the origin that gives an explicit description of what the dynamics looks like there. And then, so do the numerical computations once you hit that cube around the origin, do the explicit computation, then continue with the numerical computations afterwards.
But if the system is so sensitive to initial conditions, then how can you be sure that the round-off errors don't affect what you're looking for?
Yes, so you need to make sure that you take into account all of the rounding errors correctly.
So what is correct? I mean, if it's so sensitive to initial conditions.
No, I'll give you another example where you can see it. So take a solid torus,
Right.
wrap it into itself by wrapping it around, stretching the angle, wrapping it around twice, and contracting this way. So you get sort of a double, a thinner torus going around twice, stretched this way, contracted this way. That description is very robust. And yet what you get in the intersection all the time is a solenoid. So that's
I see.
Sorry.
So you kind of know the answer beforehand.
Well, you find a region that, like that torus with the thing is mapping into itself, and you find it stretching some part, and then that is a robust phenomenon.
So do you tinker with the parameters so that it comes out what you want?
You mean, how did Lorenz find these parameters? I don't know. I mean, he must have done some computer searches over a range of parameters, and why he picked up those particular terms. I think I read the paper once, but I don't remember.
I think, yeah, some of them correspond to some physical constants. Yes. So, yeah. These are, so the numerical bounds
So
as they were computed in Isabelle.
thing that you're looking for, is that right then?
Yes, that's what's the version of how Smale's problem is dealt with was to find some contracting directions that are invariant, and some stretching directions that are invariant, and then from that you produce some sort of dynamic conclusion sensitive dependence.
I think, I might have a picture here. So this is, so these are the bounds as computed by, so this one actually computed by my Isabelle algorithm, but the bounds for Tucker's proof look quite similar. So the attractor intersects this Poincare section here in two, almost lines. It looks like this. So this is sort of, we're looking on the top.
Geometrically intrinsic.
Yes. Some curves that are stretched.
Right.
And if we zoom in a bit more, you can see that, so the green thing is sort of the trapping region that Tucker and I attempted to verify. That's actually a trapping region. So you start to flow compute bounds starting for each of these rectangles and see where it returns. And the return is these red things.
Will you get some fractal kind of thing?
Yes, in the end, it's going to be a fractal thing. Yeah. And yeah, I mean, you said it already. Just coming up with a trapping region is not enough, because there could still be very simple dynamics inside that trapping region. It could still be just a fixed point. So that's why you also need to quantify the sensitive dependence on initial conditions. And so for every initial set, you equip it with a cone field, essentially, to show that the derivatives expand vectors in that cone field. And the cones also map into themselves. This is also done by this algorithm by also propagating the derivatives in the end. Yes. And if we zoom to the origin, so
is this a 3D picture or 2D picture?
3D. Well, it's 2D.
Well,
It's been projected from 2D.
I'm supposed to see
It's a projection of 3D. Yes. So one thing one can see here is sort of where.
So those are cubes. I mean,
it's
or rectangular blocks, three-dimensional blocks. That you show.
So very precisely, it's linear images of hypercubes. So convex sets, but often they look like cubes. And so the closer you get to the origin, the more these
Where's
sets
the origin?
here. And so this is the small part where the numerical computations don't work, where once you reach that, you do this change of coordinates and do the explicit computation. Yes, so for a complete overview of Tucker's proof, so it consists of, so that was his PhD thesis, essentially, and 25 pages of it was about coming up with this explicit formula and bounds around the origin, and these bounds you put into a computer program at the end. And then
that's a mathematical proof, probably, not a.
So this first part, that's a mathematical proof. You look at it, you can understand it, everything is fine. But the big part of the state space is analyzed by this C++ program, which the implementation of which he describes on 24 pages in his thesis. So that's already relatively complex, and it's 3,800 lines of code, which are hard to review. And it also depends on a library for interval arithmetic, which you also need to trust. So there's lots of things to trust if you want to trust this proof. And then, this program spits out a list of numbers, which sort of correspond to the numerical bounds, and then that's the proof.
And you say, no, but you check the mathematical part of this.
So what Tucker does from all of these numbers, he concludes that the return map exists, that there's a forward invariant attracting set. There's a cone field, and vectors are expanded.
Not proving that the proof is right, but verifying that it's consistent with experiments. Is that right?
No. It's actually proving the theorem. These are the properties that Tucker deduces from these computations.
If you find this cone field over a set, then by continuity you extend it.
Okay.
So you just have to check it on some discrete set of points. And you have to estimate on how many points and how far on a grid and how good is this cone field mapped into itself that you can. So there's a lot of work to do.
Yes. And then, from these properties on the return map, it's apparently relatively standard to conclude that there's a singular hyperbolic attractor.
So you do check the formal part, the mathematical part. You also check that proof formally?
No.
Too much.
It's only so much time.
I see. But then what you're really doing is sort of redoing the computation.
Right.
And give a precise description of what we need to deduce from the I'll come to that.
How does that differ from what Or Tucker did?
We'll see. Yeah. So, as I said, you might be worried about the correctness of Tucker's computations. And actually, so this is from his webpage, and there's a revision from in December 1998. He said he discovered a mistake in the code dealing with the cone field. Later, there was another mistake dealing with the expansion estimates. I mean, he fixed them, and I mean, I don't think anybody like really doubts that this is a correct proof, but still, you would like to have more confidence. Which is why I verified those computations in Isabelle. I'm gonna go over this
Now
more.
let me quote a hypothetical. Suppose you took his original thesis, would you have caught those errors?
The ones in his code.
Yeah. I mean,
No.
before he. Oh, because those are mathematical statements, and you don't check those things.
So the thing is, I
things
didn't check his computer program because I implemented a computer program myself that does the same computations. So I didn't.
Right. You know, it might be that his original bounds were wrong, and it doesn't constitute proof, but actually it's good enough. Right? But you
yes.
can't catch an error.
Yes.
There's no counterexample to his
Also, if his computer program later found some mistakes, how about yours?
Did he find mistakes?
No, he didn't.
He didn't. He just
Oh, he didn't.
mathematically found
Well,
mistakes.
he found mistakes in his code. So
Right,
his program
Right,
produced
so-
wrong bounds. Yes.
right. So what about your code?
My code is correct because I formally proved it correct.
You formally correct.
Yeah. And I could say a bit more about this, but
Formally prove the code's correct. Does that mean it's mathematically correct as well?
yes.
I mean,
It's
because
very different, though.
So
They're two
okay.
different things.
Okay.
They're two very different things.
Okay, I can come back to this in a minute.
I don't know exactly what I mean.
Yeah. So
No, but they're two different things because a mathematical proof doesn't require data representation, for example, whereas your code does. Right?
yes.
So they're not equivalent things. So proving your code correct doesn't mean that it's the same or the other way. Either way,
no.
they're two different
No,
things.
but because okay.
Yeah,
go
different
back to
but
this
in this
record.
case, it's not an issue.
What?
The representation is not difficult. The numbers and things like
Yeah.
that.
So
Differential.
No. I'm talking about the code
yeah. So
has to depend on certain data representation.
Right.
Right.
so
Whereas the mathematical proof doesn't.
I know. Yeah.
Right. So
Yeah.
so to prove that this thing is okay and to prove this thing is okay doesn't imply either of the other one is correct.
yes.
I mean,
That's
if you have both proof, then both are correct. Right? Of course.
so the thing is, so as I said in the beginning, so from the axioms of higher order logic, we developed analysis, ODEs. There's a notion of what is a unique solution to the ODE. And sort of on this abstract mathematical level, I can also prove that I can approximate this phi with, for example, the Euler method. And it's not just an approximation, I also get an upper and lower bound on the approximation error. So whenever I have something that produces an upper and lower bound, which is higher and lower, or like more conservative than the one prescribed by the Euler thing, then that's a valid enclosure. On the other side, so that's the same axioms of higher order logic.
So now, but now you have to prove something like, suppose I have a solution given to me by Euler, and I have an approximation for the derivative given to me by Euler, and there's a cone that maps into a cone, that the actual thing does the same.
Yeah.
Yes,
You have to prove that.
yes, you have to prove that.
Independent of the epsilon, basically.
And then
Whatever decision you've chosen to do the computation, you have to show the actual thing also has this property.
and
That's a different, because your computation may have been correct with your precision, but then you still need a mathematical theorem to say, that's what.
kind of,
that's
yeah.
what-
So how we relate it in the foundations is higher order logic can also be seen as or a subset of it can be seen as a functional programming language. So some of the things you can express in higher order logic are programs, and this is the programming language in which we implement our stuff.
I guess what my first question though is, suppose your program is correct in the sense the computation at the end is the correct computation. That's what it must mean.
Yes.
But it doesn't necessarily mean that it's close to what the real thing should be.
No.
It's closer to your tolerance that you said, right?
It's not just that. It's really the computation is in relation to this abstract notion of solution.
Oh, I see, yeah.
And it goes, roughly, so in this functional programming language, so you can implement floating point numbers. With this, you can implement interval arithmetic, still in the logic. And this is the program that you execute, sort of an Euler method on interval arithmetic. So this always computes enclosures.
Right.
And now you only need to make sure that the intervals that you compute here are sort of more conservative than the ones that the correctness of the Euler method abstractly gives you. And this is done by program refinement. It's the technique.
Actually, I wonder, there's I wondered about you have a dynamical system and someone tells you this is a pseudo-orbit. Then that means it's been computed up to some epsilon at each stage. How do you check that? And with another finite precision machine. This is more or less at the heart of P versus NP in finite precision arithmetic. And I imagine this program must be very expensive to check that what you've got is actually what you... if you're going to check that some output is actually a pseudo computation, must be expensive.
I mean, the computation itself, or?
Well, if someone just gives you, so at this point they've just given you a collection of numbers, and you should check that that is a computation in your system.
Okay.
I don't know how to do that.
Well, I guess the approach would be, or in this case, the approach would be to...
I'm not sure whether I may be confused. I don't think that you are talking about actually numerically computing a solution, but rather you are saying that I forgot what I want to say.
So
Sorry.
I compute numerical bounds on the solution, upper and lower bounds.
Right.
So
Exactly.
Okay.
So right.
So
I guess what I'm saying isn't exactly relevant, but it's connected.
I mean, you could sort of verify what you said. This pseudo-orbit.
So I believe your program would be saying that, okay, if you give me some initial data up to a certain precision, then I will compute, I will say that the solution lies within such bounds, close to the actual solution, right? And so going backwards, if I get that, then I can actually also go back and say, if the initial condition are given in so precise, then I will have that, right? I mean, if and only if in some sense.
Yeah.
Is that what the program actually?
Although I don't know. I think the wording with precision is. I usually think of it only as there are some enclosures. So there's an enclosure for the initial set,
right?
And then you compute an enclosure for the flow after some time.
Yeah, but I wonder. I mean, when you get, I mean the errors, the round-off error grows, exponentially usually, right?
Yes, you need to control for those round-off errors.
Well, how do you control it?
You just make your initial accuracy exponentially good.
No.
I understand.
That's really the only way.
Not just.
So you have to, when you keep tracking using interval arithmetic for the error. Wow, it gets bigger and bigger and bigger.
That's not just taken care of by the exponential growth. You just make exponentially close, you'll get exponentially, as good as you want.
Well, you only know that after you've done the computation, right? Oh yeah.
They can add. Well, depends. I mean, the estimates.
You're trying to prove,
bad.
right?
Yeah, you compute. Maybe you get better than what the estimates give.
Yeah. you get much better than the estimate, than what the estimates give you, because
extremely bad. Yeah.
because we're actually not using just intervals, but as I said, these images of hypercubes. So then you can track linear dependencies between variables. And then you also know that some errors sort of are compressed by the dynamics. That's where the system helps you actually.
Do you actually exploit that?
Yeah.
That's very important.
Yeah, that's extremely important.
So how do you systematically exploit that in a way?
Yes.
In your theory, in your proof system, how do you exploit that?
Actually, only in the implementation. So for the theory, it doesn't matter, because for the theory, all you care about is there is some enclosure.
Right.
And for the implementation, it's important that after you've done the computation, the enclosure that you get is precise enough. And that's why you can play tricks in the implementation.
So that actually needs another mathematical proof, right?
It doesn't need a proof.
Not for the algorithm.
Oh, well, I mean, you need to prove that this tracking of dependencies is correct.
Right.
This is something you need to prove. But you don't need to prove that this is much better than propagating intervals.
Okay.
Actually, if you look at Euler depending on t, as a curve in the space of maps, and you look at the flow depending on t, they're actually tangent in the C1 topology.
Oh, okay.
So then any structure that you get for one that's robust is going to hold for the other. Yeah, and that's why all this is working.
So what about besides? I mean, okay. So Euler is enough. What about these root-good four-folder?
Yes. So
have you tried that, or would it make your algorithm run faster or slower? Or?
So I use this Euler here only as illustration, or because Tucker used the Euler method. Actually. So what I'm using is a Runge-Kutta method.
Oh, you have, okay, right.
And instead of interval arithmetic, affine arithmetic. That's sort of to track these dependencies.
What's affine arithmetic?
That's not calculating with intervals, but images of hypercubes. Linear images of hypercubes.
So it's just a way allowing you to transform.
Yeah, precisely. Because as soon as you rotate a rectangle, and these linear dependencies help a lot. And
But those affine transformation can distort. So you have to show that all the distortion by the affine transformations are okay, right?
Yes.
Okay,
Yes. So you prove a library of facts about.
Turn into a very strange kind of object.
Probably what they're doing is that at each stage you look at the images contained inside a cube that's given to you by the image of the derivative. So you're only using a linear map, which you can control much better.
I mean, the simplex algorithm, for example, the cube can be distorted so that, let's say you follow the gradient method and you still go through to the end, all the vertices. So I'm not sure that, I mean, if you prove it, then that's fine, but it's not obvious that these affine transformations can actually help you.
So
I mean, for example, the simplex algorithm,
I might have
actually it's very easy. One step you go to the optimal, but if you distort the cube, then the algorithm would go through all the vertices. So how do you know that the affine transformations is going to help you control the error?
Oh, the central path will have a big derivative. You'll have to make the region very small. That depends on the composition of the linear maps.
Right.
But at each stage, you can the image of
epsilon delta thing.
The image of a rectangle is contained in the image of the derivative on a bigger rectangle. That's elementary calculus. So you can use the derivative on a bigger rectangle as an enclosure. And then you have the composition of these linear maps, which is going to have exponentially small.
Mhm.
Yeah.
So how do you map that to computer? Absolute zero may not be exceeded. It becomes zero.
Can we listen to it?
Mhm.
Can you continue?
I mean, in theory, sorry.
You have to keep.
I want to hear what you have to say.
I mean, in theory, yes, you can keep shrinking, but the computer has finite zeros.
Oh, well, no, this,
I mean,
it needs
so-
an actual computer, not.
yeah, actual computer.
With fixed
I mean,
precision.
right. You're talking about infinite precision of everything here?
Can we listen to what you want to say?
Sorry.
I have to say,
All right,
yeah,
we will.
I didn't
All right, never mind.
completely follow
It's
your
a
discussion.
Sorry.
What I wanted to say about these enclosures and how they are propagated. So we're using a Runge-Kutta method. So
Oh, okay,
so we
right,
have
okay.
an initial value and then so a linear map from something you compute here. And then there's some approximation error. The thing is, so this thing, or sort of this, the slope for the Runge-Kutta method is something, it has some linear part and some nonlinear part. And so the initial set, this will be precise. Propagation according to this linear part will be precise. And so the only things that you enclose in a cube is the nonlinear part of the Runge-Kutta method and the approximation error. And those are usually relatively small. And that's why for the largest part, you get relatively precise enclosures.
Did you try Taylor model? Next. Even more accurate.
They are more accurate, yes. But no, so I didn't try them. I had a student working on implementing Taylor model arithmetic because you also need to verify it. So that's something we've done, but we haven't tried it in the context of ODE solving yet.
My experience, by the way, is that 2 steps of Euler is
Good enough.
as accurate as the second order method
Right.
and cheaper to implement.
Wow, that's true.
Um,
So you're better off using Euler and reducing the step size.
Does it work? I mean, it seems like this is one step, right? Taking this first order.
This is one step, yes.
So is this worthwhile doing?
Runge-Kutta is the only one that Taylor methods, Runge-Kutta is more
That is better.
efficient.
That's right.
That's a Taylor, yeah.
That's maybe the best one. But beyond that, if you're looking for higher order methods and trying to use Taylor's series methods, my experience, my theoretical experience is that it takes more steps,
calculation, yeah.
more computation to achieve the same accuracy as it would by reducing the step size in the Euler method. Repeating.
That's
Here-
your experience.
Well, the thing is,
Although there are some people who really think Taylor model is the way to go.
Yeah.
but you can't, I mean, on a real finite computer, you cannot reduce the step size infinitely.
yes.
All right.
You
Whereas,
cannot.
so that's why, that's why they use the 4 order or 6 order or predictor corrector methods. Precisely because then you can use a bigger step, because they can make a bigger step.
Makes sense.
In this
I mean,
context,
that's a real computation, not in theory. If you say infinite arithmetic, then
Okay.
it's not a problem.
in this context here, so my empirical experience was that a second order Runge-Kutta method is a good choice here in this
That's
setting
the one.
because I have relatively large initial sets.
Right, that's all, right.
And
To be able to use bigger step.
higher order doesn't really help because of this non-linearization error, which is the order 2. And then if you increase the precision of the Runge-Kutta method or the accuracy, you don't gain anything because you still got this linearization error.
It's hard to tell. I mean, it's hard to tell in the end what the total, what the end error is, because it depends on the number of steps, the step size, and all that, right?
So in
Is there
all
any
of this,
theoretical, I mean, is there any theory to predict what the algebraic values are?
you can predict exponential bounds.
Right, of course. But that's pointless.
But in this case, I wouldn't know how to predict anything better, and there's also no need for it. So it's sort of you compute something and hope that you get a result that is precise enough. And in this case, you really know the precision after the computation because you get an enclosure and you know the size of this. In contrast to just computer approximations, and you never really know how precise you are. Yeah, I think could end this talk here by sort of repeating so this is the formal statement, which is formally deduced from the computations I've done in Isabelle. Says that corresponds to whatever Tucker has used there. So the return map is defined. The return map actually returns. It has some derivative. This derivative maps cones into itself, and there's also bounds on the expansions. Under the assumption that this normal form thing at the origin is correct. I think that's it. Thanks. Thank you.
More questions?
I have some question about algebra, actually, rather than this kind of geometry. You probably know Tim Daly, is that right?
No.
Tim Daly from Carnegie? No?
No, I don't know him. Sorry.
Okay. See, he is the one of the original implementer of Axiom, the scientific computation, which actually was held at City College for a number of years under Baum's law. And he is very interested in proving that the algorithms in Axiom are correct. In fact, he wants to prove it down to what he calls down to the metal, to the chip level.
Yeah.
Okay. So I was wondering whether, and of course he's knowledgeable about Isabelle and Cork and all that thing, but he's not an expert on those. Maybe you can talk to him and.
I will.
Yeah,
I didn't know that.
No, he's a Carnegie
Mellon.
Mellon.
I
I don't know exactly his position right now. I can give you an email address or something.
Do your verifications admit increasing the precision if you need to?
Yes. So, do the computations with, in the end, it's arbitrary precision floating point numbers. But sort of you fix a precision beforehand, and then you always compute to that precision. So this precision is something you can increase to your liking.
It's an entry to the program.
Yes.
Back to the algebra. So, sorry.
And then you have a checking procedure, maybe, where if the output doesn't satisfy you, you increase the precision and do the computation again? Or?
No, actually not.
No.
So I just do the computation and with the precision that, I don't know, I figured out at some point that works. And so there's no adaptive increase
So
of precision.
did you ever check that the intervals that you get may be so small that it cannot be represented by a floating point system? Not distinguishable from zero, I mean.
Don't you do big float?
Huh?
You're not limited by machine precision, are you?
I'm not limited by machine precision, but
as many bits as you want.
No, but I'm fixing a precision.
Oh yeah, okay.
But in that precision, I mean, you can never get zero, because like the worst thing that can happen is you get an interval from minus epsilon to plus epsilon. All the algorithms ensure that upper and lower bounds will always stay upper and lower bounds. end. Yeah.
I don't still understand. I mean, if your input, let's say if on initial conditions is given up to precision by epsilon, are you tracking the precision of your solution as a function of epsilon?
No. So
No. Okay.
you
What
input
do you
a
track?
concrete epsilon, essentially.
No. Or a concrete epsilon, not a symbolic epsilon.
Yes,
Ah.
it's a concrete. Yeah, but I do track the dependency on this initial epsilon in a way throughout the computations.
Of course.
But
you're
it
not
could be
tracking
that
the
it's
symbolic.
that it gets
Can
completely
you do
diluted.
symbolic computation instead? You track it symbolically?
No, not really. So all of these computations are very much tailored toward numerical, concrete numerical values.
That's because of the interval arithmetic library
Yes.
is numerical.
Yes.
So there's no symbolic interval arithmetic package?
Well, there might be, but I'm not using those.
Okay.
So
Ah,
I'm using the interval arithmetic.
I think there is.
library.
I'm not quite sure, but I think there is. You should Google it.
Okay. Thank you.